Morning, everyone. Hope we're all well today. Another hot day here in Boston. Very, very hot, warm and humid. So again, just a couple of reminders here. Okay, so exams on Thursday. A reminder that for tomorrow for homework, in addition to the homework problems, we will be doing the Turnpike City school case. It's very quick. It's going to take us probably about 5 minutes to do it. It's a very easy one. But that case will be on the exam on Thursday. So I want to make sure we cover that tomorrow. In addition, I want to make sure that students realize the resources that you have available to you on Questrom tools, okay? I did post under the Parker problems, I posted all those problems that deal with hypothesis testing, right? In addition, there's also, I think there's also on the website another set of errors and p-value problems, right? Along with the answers, okay? So I've made sure everything's up to date. All the homework solutions have been posted, right? So the website has a lot of good information for you to catch up or study, et cetera, et cetera. So you should be in good shape for that, okay? All right, so today, like I said, the homework today is not gonna take us that long to do. On two sample testing. So give me a second to give this kind of ready, and then we'll get ready. So give me a minute here. Just put this up. That. Yeah. My apologies. My document camera on. All right, all set to go here. Waiting for something to print here. So all set to go here. Get my document camera ready. My printer is thinking. Takes time.
Professor.
Yes.
So the Turnpike school case is the only case that the final will include.
Yep, that's the only case that's going to be in the final.
Okay. And all right, thank you.
Oh, all right, taking too long. Okay, so if you look at the problem, I was going to show you the problem, but my printer's not working, so I'm not going to wait for that. So let me put together, show you my Excel here. Right. So basically, we're told with this problem. Everybody can see the Excel, thumbs up. Thank you. Okay. So we're told that the coach of a basketball team, he wants to improve his players' free throw shooting. So he wants to put together a hypnotist. So he has them, they go through the program. So they take 23 throws and we record how many they get in. And then they do, under hypnosis, they take another 23 throws to see how many they get in. So here are the results before and after. Okay. So again, one of the challenges that you have, as was with the first test, was to understand what kind of problem it is, right? So, I told you Bayes rule. If you see the words given, 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 all that sort of thing, it means it's a Bayes rule problem, right? Or if you see the word given, it means it's some kind of conditional probability. I told you that magic word within. If you see something within, usually that refers to the variable lowercase e, which stands for the margin of error, et cetera, et cetera. So the problem like this, you've got to make sure to understand that you're looking at the same people a second time or multiple times. So therefore, it's not a different sample size, or excuse me, a different sample group. It's the same size, but different group. So therefore, it is, it's the same 7 people. So this is what makes this a paired T test. Okay, so we're going to do this using Excel. Okay, and again, as I mentioned, we're going to use the Data tab and go over here and do this thing called Data tab and do data analysis. Okay, and we're going to go down here and use the T-test paired two sample of means. We click OK. Okay. The variable range is going to be the pre-hypnosis. Actually, what I'm going to do is I'm going to make the first one. You can do this either way. It just matters. It just makes a difference whether you get a negative or positives. Again, you're looking at the difference. I want the differences to be positive. So I want to know whether actually the difference is greater than 0, right? I want to know the difference greater than 0. So clearly, I want the pre-hypnosis to be more. So that's going to be my first column because it's going to take one. It's going to do column 1 minus column 2. Okay. So I really want, I want this to be the post-hypnosis. It really doesn't make a difference. If you understand you get a negative, you did it the other way, which is fine. Okay. So that's that one. And then I want my my second variable is the pre-hypnosis. Okay, and again, I click off the labels. By saying labels, it tells us that the pre-hypnosis and the post-hypnosis, I've brought them into the analysis, and Excel will knows to ignore those cells because he knows they're not data cells. All right, the hypothesized mean difference again is going to be 0, right? And our alpha in this case, looking at the problem, is 0.01, right? So 0.01%. We want to have a new worksheet, and we click OK, right? And here's the next thing. So I'm going to change this to 118 output, right? So I can label my tab across the bottom. Again, let me make this bigger so we can all read it. All right. And let me just make my okay. And again, I always like to make the data a little easier to understand. So I like to don't have to have so many decimal places. Okay. All right. So here's our output. I am going to print this so we can basically do this on my document camera as well. All right. So obviously, this is the mean of the first group, right? 16, right? So that's obviously this average here. Okay. The 14.47, oh, no, post-hypnosis, I'm sorry, it's post. Sorry, it's the mean of this one, it's the mean of this column. The pre-hypnosis, again, that's the advantage of putting the labels in, is when you get the output, it'll tell you which column is which. So that's why I like when the label's in here. So this is the mean from the other one, from the pre-hypnosis. So this column here, okay. The variance, remember the variance is S squared. So this is the variance for the post-hypnosis. Here is the variance for the pre-hypnosis, okay? The observations obviously is 7, right? Forget the correlation, we don't care about that, right? So we can ignore that now. The hypothesized mean difference is 0. The degrees of freedom, remember the degrees of freedom is only 6. So it's not 7 in one group and 7 in another group. So you don't do 7 minus 1, 7 minus 1 have a difference of 12 degrees of freedom. It's only 6 because it's the same group of 7 people. Okay. Your t-stat again, remember that's step 3. That's your t-test, right? Your test statistic. So that's where you're doing x bar 1 minus x bar 2 all over SP, 1 over square root of n1, 1 over square root of n2, correct? We're looking at a 1 or 2 tail test. Clearly this is a 1 tail test. So we're looking at this information here. So this is our critical. So our critical point is 3.143, right? 2.56 is less than that, so we're going to accept HO. Okay, so I'm going to switch my document camera. That's basically the same thing as this printout, so I can mark this up. So let me do that for everyone. All right. Can everybody see that okay? Thumbs up. Everybody see that nice and clear? Okay, good. All right, get my light on again. Again, as I mentioned, this is what I made pre-hypnosis. So this was actually my column 2, and this is my column number 1. Okay, so it doesn't make any difference how I do this, but especially if I keep my column numbers correct, this is x bar sub 2, this is s sub 2 squared, this is n2, right? This is x bar sub 1, this is s1 squared, and this is n sub 2. Again, they've got to be the same. It's the same 7 people, right? Pearson correlation, again, we don't care about that. The mean difference, we put that in 0. Degrees of freedom are just n minus 1. Again, the t-stat. This is our step 3, okay? So what we have is, we have this. We know, ba-ding, right? We know, we want to know whether it's greater than 0, right? We want to know whether D bar is greater than 0. So clearly that's a ba-ding, that's an upper tail test, right? This is 0.01. So this value here, so we can forget this two-tailed test here. We don't care about that, right? So what we want to know, we want to know this value here. So that value here is 3.143. Our T-stat, which is step 3, is 2.569. That's here. Clearly, it's going to be accept HO. Okay? So accept HO means it doesn't appear that it worked, right? So because H1 is it's greater than 0, right? So less than or equal to 0. So except HO, it doesn't appear the difference. So the hypnosis did not work. Okay. Okay. Looking at this is our p-value. Our p-value is 0.021. Our alpha is 0.01. So again, p-value is greater than or equal to alpha except HO. So looking at p-value is also a way to do this test. Any questions?
Professor, are we going to have to do the Excel way on the exam, or is it just like for us to know, like just for life?
You're not gonna need to know. Again, I can't ask you. Excuse me. At this point in this course, I cannot ask you to use your Excel on the computer. Now, we're obviously with this pandemic, we're doing a lot of things online. So I wouldn't say in future courses or future classes of this, or future sections of this class, we won't have you do Excel, but for you, you won't have to do that now. What you might do is I might have you do it by hand, which I'm gonna show you right now.
So we might actually get questions on the exam that would give us multiple different data points, but then we would just have to do it by hand.
Correct.
Okay.
I'm going to show you. I'm going to show you exactly. As a matter of fact, we are going to have a quiz on this. Not today. The quiz is going to be tomorrow. So the quiz tomorrow will be on this topic, and that'll be a good example of what you might see on an exam. Okay. All right. So I want to reiterate with you what I've said before. You really want to know what p-value is, right? Or know how to use p-value. Like I said, in this class, we primarily are just looking for you to know how to calculate it. And yes, I just showed you how you could look at compared to alpha. That's a very important thing. Because leaving this course, as I mentioned, many of you going into business, you will definitely 100%, I guarantee it, in your career, someone is going to talk with you, or you're going to go to a seminar, or someone's going to talk about data and talk about regression analysis or data analysis. And in their analysis, they're probably going to talk about p-value. It is a very, very common term in data analysis, okay? So you should, p-value isn't something where if somebody says it, you shouldn't scratch your head and say, oh, what's that? That would be bad, right? If I were interviewing you for a data analysis job and you had never heard of p-value, clearly I would say you know nothing about data analysis, you're not being hired, right? So again, like I said, you don't need to be a expert, but you should know what p-value is and know kind of what it looks like. Again, it's always a good reference for p-value compared to alpha, right? So you want to make sure you know that. Okay, so what I want to do is I want to go back to my screen share with you. 1 second, trying to try to manipulate multiple screens here. All right, so let me go back to my screen share. Okay. All right. Okay. So if we were going to, let me go back to the original problem. If we were going to do this by hand, okay, Now, for instance, what we would do, right, is we would have to do the difference of these two cells. So what I would do is I do equals, let's see, let's make sure it's the same size. Okay. Let's try and make this the same size so you can see the data. Okay. So if I do equals this cell post-hypnosis minus pre-hypnosis, which is what we did, you get a difference of 2. Then I can grab this all the way down here, and this gives me my differences. Then what I can do is I can do, from the home button, I can do over this thing auto sum. I can have the average, and I'm with the average of that column, and my average is 1.6. So this is my D bar. Okay. Then what I can do is I can do the command equals STDEV, standard deviation of this group, 1.6. Right. So that's Huh. I'm very suspicious they're the same number, but maybe they are. All right. So okay. Essentially, what I could do is I could give you a problem that has all of this. Okay. So this number here, to do it by hand, I would give this to you. This number here, I would also give it to you. So I'm not going to look for you to calculate the mean, although I should. But again, we're trying to make it fair for those people that have special calculators and those that don't have special calculators, right? So I should be able to give you D bar, and I should also be able to give you the standard deviation of D, right? And then what you should be able to do is to calculate it out. Okay, so let's do that. Okay, so let me go to my document camera. Stop sharing. Okay. There we go. A little bit better here. All right. So what we have HO and H1, right? We want to know whether the mu is greater than 0, less than or equal to 0, right? We're going to reject HO if T-calc is greater than some number, okay? So we know our N is 7, so therefore our degrees of freedom are 6. We know our alpha is 0.01. So degrees of freedom are 6. One-tailed test, 0.01. The first column, by the way, is 0.1. 0.01 is this column over here. It's the fourth column, okay? Right? So 0.01, we go down to our degrees of freedom. There's a value 3.143, which is the same value we got with Excel. 3.143. Then we do our test statistic, which is going to be our D bar. Our D bar was 1.6. Our S sub D is also 1.6. So it'd be 1.6 minus 0 all over standard deviation is 1.6 square root of 7. So 1.6. Someone do this for me. What is 1.6 divided by square root of 7? I don't have that calculation right here.
It's 0.60. How many decimal points you want? 47.
I'm sorry, say it again. 0.6?
Yeah, 0.6047.
Okay. So 0.0. So then what is this fraction then?
$2.64.
2.62?
4.
64?
64.
Okay,
Yeah.
64. Okay. So again, $3.143, 2.64 is here, except HO. Okay? Basically, this almost the same thing we have here, right? Right. So they have 2.59. So it's close. I'm not sure my math may have missed out something, but clearly it's the same. It's the same way. This is the way you get it. Okay. So doing it by hand, you're just doing a straight t-test, right? You're not doing a 2-sample, so you're comparing it to 0. So that's why this is your x bar minus 0, and this is over your standard error, which is S over square root of n. So we do the exact same thing that we've done when we've done this other times in class for hypothesis testing. Questions?
So, Professor, I have a question about the first step. The first step is H0 mu less than or equals to 0. 0. Is that like, do we put 0 because it's pool, or?
Yeah, basically what you're doing is you're trying to do. You're trying to see whether you're really trying to see whether you're trying to see if D bar is greater than 0. Is what you're trying to do. You're not trying to mute. You're trying to see if the difference is greater than 0, significantly greater than 0.
Okay, to see if it's improved.
Right. Yeah. Right. Right. You want to see if the hypothesis, see what hypnosis has worked. Any questions from the audience? Okay, let's do the next one. We'll do the exact next one same way. There's only 2 problems. Okay. So let me. So the next problem. Okay. Liam. Here we go. Liam and Will are convinced that the Rentham House of Pizza delivers pizza to their house quicker than Domino's. They decide to order the same pizza from both businesses 5 different nights, the same time of the evening, right? They record the time it takes pizza to be delivered in minutes, sometimes and below, right? So they're trying to see whether Rentham House of Pizza is quicker than Domino's, right? So this is they want to know whether so this is less time than this one, okay? So here's the night. They were the same pizza. This is how long it took, okay? So again, and alpha is 0.05. Okay, so let's go back to the Excel, and then we'll come back and do it individually as well. So let me go back to my screen share. Okay, here's my other problem. Okay, so here's the night. Here's the information from the Rentham House of Pizza. Okay. Now again, we're trying to see basically what we're trying to do. If for rent them to be quicker, that means dominoes is going to be greater, right? So again, I'm going to do the exact same thing. I'm going to, when I put this in Excel, I'm going to put this as my column 1 because that way I get positive numbers. Again, it doesn't make any difference. You have to just understand whether you're doing positive or negative, you get the exact same things. Okay. All right. So again, what we're going to do is we're going to do our data. We're going to do data analysis. Now again, it's already, it defaults, because I just used it, it defaults again to the t-test paired two-sample of the means. I click OK. Now I'm going to do Rentham House, my dominoes. I grab that. I click off my labels. I click the other one. I grab Rentham House. Press Enter. I have the label checked off. My alpha is 0.05. In this case, back to the default. We're going to put it into a new data range, and we just click OK. And again, I'm going to edit the name of this. This is 119 output. Okay. Let me make this larger. Make the files. Right. So again, we don't have this many decimal places. You'll find that you'll find that I'm one of the only professors that does this. I like to truncate the decimal places so you don't have so many, because there's no reason to have 12 decimal places. I just find it to be sloppy, and I find it to be, it's confusing because you have too many numbers, right? So you don't, again, we're not building rockets. So I know some of you are taking me for 222, and you'll see that when I do these things in class, I will truncate the decimals, but on exams, again, I don't necessarily write the exams; they're done cumulatively. A lot of professors, we all kind of contribute, so you may see a lot of extra decimals. But again, the idea is try to ignore them. Right? I think it's a sloppy way to do it. But all right, so here we have some stuff. So again, these values here, clearly those are respective x's, x bars, right? These are the variances. Remember, these are the variances, so this is s squared, okay? And the observations are 5 and 5, right? So there's only 1. Forget about the Pearson, right? Degrees of freedom are 5 minus 1, 4, right? This is a one-tailed test again, because we're not seeing whether they're equal or there's a difference between the two. We're talking about whether Rentham House of Pizza is quicker than Domino. So it's a one-tailed test, okay? This is our t-stat, right? So this is the step 3, and then we can forget the stuff across the bottom. Forget that stuff there. We don't care about the two-tailed test. The other number we're going to look is this one right here. Is 2.132. Okay. So again, let me print this out again. So then we can talk about it. To see if we get the same answer. So clearly in this one here, our t-stat is 0.9. Clearly that's less than 2.132. We are going to reject HO. Accept HO. And accepting HO means Rentham House is not quicker, right? So it's going to be greater than or equal to. Let me show you my document camera again. Okay, make this a little bigger here. Right. So again, dominoes, right? This is right. So we basically want to know whether Rentham House is less than dominoes, meaning it's quicker, right? But I want to get a positive number, so I switch these. So it's really going to be whether dominoes is greater than Rentham House, right? So it's greater than. Okay. So again, so this is my x bar sub 2. This is my x bar sub 1. This is my S2 squared. This is my S1 squared. This is my N1. N sub 2, sorry. This is my N sub 1. We don't care about the Pearson. The difference is 0. The degrees of freedom are N minus 1. This is a one-tailed test, so we don't care about this, right? Because your HO and H1 is whether D bar, this is less than or equal to 0, D bar greater than 0. Okay? So what we have is, we have our chart here, right? This is your critical point. This is 2.132, where this is 0.05, and 0.9 is here. We're going to accept HO. HO, not quicker.
I have a question.
I have an answer.
So like obviously these data sets are not from the same, same store. So why are we using the paired one?
They are the same store. It's the same. It's the same Rentham House of Pizza. It's the same Domino's. So essentially, really, what you're doing is the data set is really the N has to do with the 5 nights.
Yeah, I get it.
Okay. All right. So you could see a problem like this, but what's missing is I'd have to give you D bar, and I'd have to give you S sub D. Right. So let's go back to Excel. Again, you would not need to do that. I'm just showing you what I would have to provide for you. Okay. So again, all right. So this, we want to do the difference. So what I would do is I'd do this minus Rentham. Okay. Then I would give you the average. Geez, 1.6 again. That's funny. Okay. Then I would give you the standard deviation. Four. Okay. So this is your D bar. This is standard deviation. Okay. So I gave you 1.6 and 4. All right. So let me go back to my document camera. Stop sharing. So our D bar was 1.6, standard deviation was 4, right? So again, our HO and H1, right? We're going to say whether D bar is less than or equal to 0, D greater than 0, T bar greater than 0. You're going to reject HO if T-calc, again, greater than some number. It's going to be upper tail test. Okay, so N is 5, so our degrees of freedom are going to be 4. Okay. Oops, don't like that one. Okay. So one significance scale for one tail test, 0.05, this one here. Degrees of freedom are going to be 4, 2.1, 2.132. Right? So I'm going to draw this over here. This is 0.05, 2.132. Right? Step 1, step 2. Step 3 is going to be 1.6 minus 0 all over your 4 over square root of 5. Right? So 1.6. What is 4 over square root of 5? And then what is it? Someone tell me that calculation. See if it indeed is 0.9.
Could you zoom out a bit?
Yep. Oh, sorry. Yep. What is the 4 square root of 5?
I got 1.78.
1.78. Okay.
Yeah.
Good. So that's what's 1.6 over 1.78, which is close to 1.9, isn't it?
It's like over. That's like 0.89 or 0.9.
0.9. Okay.
Yeah.
Good. Close enough. Okay. So again, 0.9. You're going to accept HO. HO is that it really is not a difference, right? It's not really greater than 0. So your conclusion is Wrentham house not quicker than Domino's. So I say again, on an exam, you could have this problem, but I would need to include, you would not need to do this. I would give this to you. I showed you how to do it in Excel just so you know where the numbers come from, right? I don't like students to just think that numbers kind of appear. I like to show them why they're there, right? So we found the difference, the average difference, and we calculated the standard deviation of the average difference. This is standard deviation of P bar. Okay, any questions? Everybody good?
So in this case, the mean is the second mean. I mean, it's 1.6 minus 0 that you wrote, right? So the second mean is always 0, or is it just for this case?
What do you mean? No. It's whenever you do paired data, it's almost always you're looking at whether or not the difference is greater than whether it's equal to 0 or it's greater than or less than 0.
Because the third step, when you were doing the equation, the 1.6 minus 0.
Right. It's always x bar. It's the same equation. It's the one we've done before, right? It's the one we've done before where it's always your T-calc is always x bar minus mu over S over radical n.
Oh yeah, the mu is 0.
In this case, x bar is going to be minus the 0 because that's what you think the difference is, all over S over radical n.
Got it. Thank you.
You're welcome. Okay. All right. So again, that's it for the homework. Okay. So, and we have a pretty big lecture to go to today. So, do the key points of the day, little assessment there, and then we'll take a break and we'll come back and talk about our 2 topics today having to do with the chi-square test of goodness of fit and test of independence is the last two topics you're going to learn for this course, right? So we're wrapping things up, right? So I'll see you all in a few minutes, okay? So I'll put the camera on, and we'll go from there. Welcome back, everybody. Probably will have my snack. Waiting for everybody to put their cameras back on. All right, before we begin our last topic, I just want to say thank you. I certainly appreciate everybody coming to class every day. I know it wasn't easy for this. A lot of people are just watching recordings. I get it. We're all getting by as best we can. Certainly, I'm very impressed with all of you, actually. I've had some great meetings with students outside of class talking about problems. And again, a lot of you have come to see me in office hours and met with me outside of class. That's great. Others of you haven't, that's fine too. It's whatever makes sense for you. And hopefully, if I haven't been able to help you, hopefully Lucas has been able to help you. But the level of understanding, I think, is great. And certainly that's a test to you, because obviously you guys have really done really well on both exams. So I'm fully anticipating, the final will probably be the same way. So did well. So we've done a lot of things, right? So we talked about, probability and how that works through, and then talk about sampling, then this decision analysis or the decision trees, and talk about all the different distributions that are out there for different types of data, for the Poisson and the binomial, and then talk about the normal curve and the properties. Again, you're going to use the normal curve a lot, right? Because again, why is the normal curve so important? It's so important because of the CLT, right? Because again, if you sample something, only 15 sample sizes, or 15 members of a sample, I guess, by default, it becomes a normal curve. So therefore, you can use a lot of the theory and a lot of the things around the normal curve to make predictions. That's great. I had somebody you know, I had a graduate student reach out to me, you know, just like 2 weeks ago, somebody that I had a few years ago, and they had a question with their work where they were trying to talk about, they're trying to do some data analysis, and unfortunately they're, you know, they had so much data, but it was taking too long to crunch the numbers. And so we had our conversation about what they could use for sample sizes and still be confident. So I had that whole discussion with them to make sure that kind of works. So that was great. So, I mean, I really appreciate you guys showing the effort. And again, what you're learning in this course is real world data or real world knowledge that you can then take with you to go somewhere else. Right. So again, as I mentioned, and I'll talk about this tomorrow too, as to kind of our wrap up, is, you know, this is a burgeoning field. So, you know, again, thank you for coming again, and certainly putting up with my quirkiness and stuff like this. I've had a few issues with some of the recordings, but we're trying to make sure it all makes do. And hopefully, hopefully you see the learning that I'm doing by, you know, the quizzes and the key points of the day, right? They're all ways to help you prepare yourself with knowledge to make sure you're better. So certainly, you know, things are wrapping down. You'll be done the end of this week. And then you're off for a couple of weeks, and then we start all again beginning in September, where whether or not you're on campus or remotely. So it'll be great. So certainly. So thank you all for coming. All right. Any questions before we begin our topic? Okay. Then I will screen share with us, with all of you. Okay. So this last topic is called the chi-square test. Now, in some semesters, I cover this over 2 days. In some semesters, I cover it in 1 day. This semester, I'm going to cover it in 1 day. Okay. You know, when I've taught this course at other institutions, I've taught a version of this class at Babson and some other places. We talk about the chi-square test. We do them all in 1 day. So I'm not necessarily overburdening you with this. Okay. Now, one of the things you need to keep in mind with this topic is, again, this is another topic where you've got to make sure you understand what's being done or what the question is asking you, right? So part of the challenge that you will have in taking the exam on Thursday is being able to read a question and from the question determine what kind of problem it is. Okay. Because if you start going astray, then you're going to get the whole problem wrong because you're going to be going the wrong way. Okay. So there are several chi-square. Now, chi-square is the X, the Greek letter X with a little tail on it. There are several chi-square tests. We're going to learn 2 of them. One is called the chi-square test of independence, and the other one is the goodness of fit. We're going to start with the goodness of fit. There's a third one that's pretty common called the chi-square test of homoscedasticity. We don't talk about that one, but there are other ones, right? So the chi-square really is a way of looking at the least squares, and I'll talk about this in general when I start talking about this. Okay. So the goodness of fit test, again, this is the first one. Goodness of fit test is a test that inquires whether or not the body of data can be reasonably viewed as being generated by a distribution. So in other words, if you assume that you have a store and you're saying that, okay, 20% of the people are paying with cash, 50% of people pay with a check, and the other 30% pay by credit card, again, you could do it. You could look at a test to determine whether or not indeed people are paying in those proportions, right? Whether or not they are paying in that, following that model: 20 credit card, 50% cash, 50% check, and 30% debit card, or whatever I said. Okay, so you want to know that. Okay, so the interesting thing about this distribution is HO and H1 is always the same. If it is a chi-square goodness of fit test, you do not need to go through all the machinations to determine what is HO and H1. It is very simply HO, the data is generated by the distribution. H1, the data is not generated, right? So I'm going to let you say the following. Please listen to me. I'm going to let you say HO, data follows the model. H1, data does not follow model. I'll say it again. For these types of problems, there's only one hypothesis statement. And the hypothesis statement is the following. HO, data follows the model. H1, data does not follow the model. Third time, HO, data follows the model. H1, data does not follow the model, right? It's an easy way to do this. So to be official, the official way of writing it, you say, oh, HO is that, you know, customers follow the distribution of 50% cash, you know, what did I say? I said 20% credit card, 50% check, and 30% cash, right? That's officially what you'd say, but you don't have to say that. All you have to say is data follows the model, data does not follow the model. Okay. Now the chi-square distribution, right? Developed by this guy Pearson, where that Pearson test came in from the on the Excel we looked at beginning of class today. Okay, so it looks kind of like the Poisson distribution, meaning it's not normal. Clearly, you follow the way my pointer's going. It's very steep at the beginning and then it kind of tails off to the right. Okay, it is not symmetric. I repeat, is not symmetric. Definitely skewed to the right, and it's non-negative, meaning where the pointer is right now, that is the 0 point. Because clearly what you're doing, you're squaring something. And when you square two negatives, what do you get? You get a positive, right? So there are no negatives, right? Non-symmetric, skewed to the right, non-negative. And just like the T-curve, where the T-curve is actually a family of curves that depends on degrees of freedom, the chi-square test, the chi-square distribution also varies. So again, how you look at or how you read the table, and again, there'll be another table, I'm going to show you that in a minute, another table. How you read the table depends on the degrees of freedom. Okay, so for the final, you're going to make sure you know the Z-chart, and you should know that by now, front and back, right? You should know how to find values in the body of the table, in the middle part, and be able to translate it to the margins. Find from the margins, find the body, et cetera, right? So you should definitely know the Z-curve, right? How to read it without a doubt, without any mistakes. And also, we've done the T-curve now enough that you should basically know how to read that and know how to use that well. You're going to have a couple of days to know how to do the chi-square test, the chi-square table. It's pretty easy. I'll show it to you in a minute. It's not really as difficult. It's a lot easier than the T, right? So that'd be easy to do. So you have to know all three of them, okay, for the exam. My strong suggestion, again, all three of these tables are available on Questrom tools. I would print them out if you have a way to do that, or have them by you, so that way you're not digging for them, right? If the final exam, again, is timed, right? So you're gonna need to get things done and work at a good pace. Okay, so again, non-symmetric, skewed to the right, non-negative, right? Kind of looks like the Poisson curve. Okay, so let's consider something, right? So my example was a shopkeeper and the number of customers. Here we've got something else. Let's say we've got a group of items and we're saying, okay, 80% of them are deemed as good, 15% are deemed as fair, and 5% are deemed as poor, right? So this essentially is the model, right? This is the model. So we want to wish to inquire whether the data we have on a product quality is consistent with the above model, right? So we're going to get what? We're going to get a sample, right? So hypothesis testing always deals with grabbing a sample and then making some kind of assertion or some kind of test around that sample. Again, here's the official verbiage that they have for HO and H1. I will repeat myself. All you need to write is HO, data follows the model. H1, data does not follow the model. Okay? On an exam, I'm not even sure I'm going to ask you to write it. You may just say HO and H1. Okay? All right. So then this information that I'm circling with my laser pointer is the data, right? So this is the sample. Okay, this is the sample. So we sampled 120 items, we determined 86 of them were deemed to be good. 25 of the 120 were fair, and 9 were poor, for a total of 120. These are known as your observed values, and it's O sub I. Don't worry about the I per month, but it's observed. It's observed, okay? Now what we need to find out is we need to find out, well, okay, based on this model, right, on this model, we thought 80% of them were going to be good, 15% were going to be fair, and 5% were going to be bad, or poor, rather, okay? So then what we have to do is find out, okay, based on our model, what were we expecting to get from the 120? So 120, right, we were expecting 80%, so we were expecting 96. We only get 86. Huh. 120, we're expecting 15% to be fair. We get 18. What did we get? We got 25. Huh. We were expecting 5% of the 120 or 6 to be poor. We got 9. Okay. So these numbers up here are, again, are your observed. These ones right here, the 96, the 18, and the 6 are what? Are the expected. So you have observed values and you have expected values, right? Common sense suggests that we examine the differences between the two. Exactly. Okay. So then what we can do is we can calculate this right here is our chi-square calc, right? Chi-square calc. Now, what we've learned in hypothesis testing so far, step number 3, right? We did a z-calc and a t-calc. Now we're learning the chi-square calc. The chi-square calc is simply this. It's the observed minus expected squared divided by the expected. Observed minus the expected squared divided by the expected. And you do that for each data point. So in other words, the good is 86, that's our observed. The good for expected is 96. So we do 86 minus 96, observed minus expected, 86 minus 96, which is 10. You're going to square that, which is 100, and then divide that by 96. 100 by 96. So you're going to get that value. And then you're going to add 25 minus 18 squared divided by 18. You're going to get that value. And the last one is going to be 9 minus 6, which is going to be 3, squared, which is 9 divided by 6, which is 1.5. Okay, so essentially what we're going to do. So again, observed minus expected squared all over expected. Okay. Now, the degrees of freedom. Degrees of freedom. For the t-curve, we did n minus 1. N, sample size minus 1. The degrees of freedom here are denoted as k, not n, k. And k represents the number of categories. In our example here, how many categories do we have? Well, we have good, fair, and poor. We've got 3. So minus 1 is 2. So our degrees of freedom that we're going to use for this problem right now are 2, right here. K minus 3. K minus 1. 3 minus 1 is 2. So then the next slide, here is the chi-square calc. Again, it was 86, which is the observed for good, minus the expected for good. 86 minus 96 squared, that's 100, divided by 96, right? That's 104. That makes sense, right? 100 divided by 96 is 104. 25 is the observed for good, minus the 18, which is expected for good. Square that, divided by 18, that's 2.72. And again, 9, which is the observed, minus the expected of 6 for fair, right, is 3. 3 squared is 9, divided by 6. 9 divided by 6 is 1.5. You add them all up, and you get 5.26. 5.26 is your chi-square calc, just like we did z-calc, just like we did t-calc. So then what we have to do is we have to look at 5.26 and look at that where it stands on our chi-square chart, which is on the next page. Okay. All right. So what I'm going to do is I'm going to show you my document camera because I have a chi-square chart that you'll be able to see a little better. Okay. I'll zoom in a second. But this right here shows you it's a family of curves, right? So basically it starts like this. And then if your degrees of freedom get bigger, it's going to be more like this. And then, you know, it's really going to change. But again, it's always going to be very, very much right skewed. Okay. It never, the T curve will eventually look like the Z curve. The T curve will look like the Z curve. The chi-square curve will never. It always looks like this. Always it's going to be a lot of values to the left side and always will tail off to the right. Okay, so let me go a little closer, right? And again, you need to print this out, okay? So this right here, right? This column here are your degrees of freedom, just like you had in the T-chart, okay? It doesn't go up. It doesn't go up by ones, right? It goes 1 through 5, 6 through 10, 15, then to 20, and then 25, then to 30, and then it goes up by 5s, 35, 40, 45, 50, 55, right? So obviously, I will need to give you, this is a sample chi-square. I'll have to give you something that obviously you can read on this chart, right? Obviously, the whole thing is much more difficult. And then your alphas, 0.1, 0.05, 0.025, 0.01, 0.005, and 0.0001. Now, clearly, we've never really done these for alphas, right? So clearly, we're probably going to do this column here, right? We're probably going to do this column here, and we're probably going to do this column here. So we're probably not going to do this column, this one, or this one. I don't think so, anyway. Again, I haven't put the exam together yet, but I'll find out what that is. Okay? So for our value, what did we determine it was? This was a, it was three categories minus 1, so it's 2 degrees of freedom, 0.05, 5.99. 5.99. So for our drawing, again, it looks like this. Our cutoff was 5.99. The value we calculated based on our was 5.26. So 5.26 is here. We're going to accept HO. Oops, sorry, my pen's dying here. Throw that one away. Going to accept HO. Data follows model, meaning it does appear that it's 80%, 15%, and 0.05%. So this is good, this is fair, this is poor. P-value. P-value, the command is right here. It's chi-dis. Just like the T curve, you don't figure it out, it's chi-dis, and it's your cutoff, 5.26, and then the degrees of freedom. Degrees of freedom in this case is just 2, right? And this is actually the example they give you right here, 5.262. So that equals your p-value. Chi-INV, you don't need to do that. This is the one for p-value. Okay. So again, your chi-square. Chi is that, chi-square. This is x squared. Chi is this thing with a little tail on it. right? So it's not x squared, it's chi-squared, right? So your chi-square calc is observed minus expected squared all over expected. And it's the sum for all the data points. That's what it is. Observed minus expected squared all over expected. Very easy. Any questions so far? All right, let me go back to my screen share with you. Let me have my sip of coffee here. Show me the love. Everybody wave. Let me know you're there. Raphael, you awake? Right? Everybody wave to me. Thank you so much. Again, I'm in a room, feel like I'm talking to a box. No one knows what's going. Xiao Yu, thank you. Saw your waving hand. Okay. Any questions so far? All right, let's do another problem. Okay. So here's, again, you can use the chi-square in many different examples. Okay. So let's show this one. This was a little complicated, but it makes a good example. Here, we're looking at the number of flaws in the square per square yard. So this one, we're assuming, you know what? What if we're trying to determine whether the model is a Poisson? Again, the Poisson is a distribution. We're alleging that the rate of flaws follows a Poisson with a mu of 0.9. Therefore, H1 is it's not Poisson with a mu of 0.9, meaning data follows the model, data does not follow the model. Data follows the model, data does not follow the model. In this case, the model is a Poisson. Okay, so again, here what we have our observed frequencies. Okay, so again, we took 150 rolls, I guess, or 150 yards here. We found that 68 of them had no errors, no flaws. 51 had one error. 19 had 2 flaws. 9 had 3 flaws, and 3 of them, and there were 3 that had more than 4 or more. Okay, so these are what? These are our observed. These are our observed frequencies. Then we have to come up with our expected. Well, the thing is here, there's something that's a little unique about the Poisson. So again, if you do Poisson 0, 0.90, you're going to get 4066. You're going to multiply that by the 150. So you're expecting 60.99. You got 68, right? So you observed 68. The expected was 60.99. For the next one, it's Poisson 1, 0.9, 0. How likely will you get exactly 1? That's 0.3659. Multiply that by 150, you get 54.89, et cetera, et cetera. All right, let me talk about what's happening down here at the bottom, right? That I'm drawing a rectangle around with my laser pointer. Well, the thing is, we can't just use 4, 5, and 6 because we stopped counting at more than 4. So really what this has to be, this can't be 4, 5, 6, 7, 8, 9, 10 individually. It's going to be just more than 4. So this Poisson down here where I'm circling with a laser pointer really is going to be 4 or more, which is 1 minus 3 or less. So that would be 1 minus Poisson 3, 0.9, 1. You'd get that value, and that value is 0.0134. And you multiply that by 150, and you get the value roughly of 2. Okay? All right.
Professor, what is the Poisson table?
The Poisson table, not Poisson table, it's the Excel command. You know, remember we did Poisson when we did in class? There is a table, but we no longer show it in this class.
So when we're doing a question like this, we'll have to.
You'll never do a question like this.
Okay.
Right. Again. So, but again, I want to make sure, you know, I want to really understand my role. I'm not just showing you things that's going to be on a test. I'm showing you things to know the theory. So this specific question will never be on a test. But again, I'm trying to show you that my point of going through this example is to show that the chi-square example, it doesn't need to be about something simple. It can be around a complicated distribution, right? To piggyback on Ashley's comment, same thing. Remember the other day, we did a problem that was a beta problem, a type 2 error problem that was around the Poisson, right? For the number of people going to a restaurant, I think it was problem 106. Good example, right? So again, you gotta understand that we can use past information or past theory in this class to talk about things. It just so happens that this one, we're using it to see whether the data fits the model, the data does not fit the model. In this instance, the model is a Poisson. Okay. So let me make a quick comment about something. Again, there are things that we learn. There's a reason we learn things in this class in the order that we learn them. If you, let's say right here, everybody sees what I'm doing with the laser pointer. I'm circling the x equals 4, and I have the value of 0.0111. Let's say you were actually doing this problem, and let's say, okay, Poisson 0.90, Poisson 1.90, 3, blah, 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 and you go to 4, and you go Poisson 4, comma, 0.9, comma, 0, and you go 0.11, and you go, okay, and you do your math, and you get your answers. There's a way you can check to make sure you did it right. It goes back to the first class. What was it? This notion of being collectively exhaustive, meaning that you've got to account for everything and that the sum of all the probabilities must equal 1. If you added up 0.4066, 0.3659, 0.1647, 0.0494, and 0.0111, you would find what? They do not equal 1. You're missing something. That's why you need to truncate, you need to collapse the table, they say, and count this last value is things 4 or more. That's the first comment. And again, this is kind of an aside about the Poisson. Am I going to test you on this? I am not going to test you on this. But remember my role is to teach you statistics. The other thing that you've got to do about this is understand that with the chi-square calculation, you've got to make sure that your expected, you really don't want your expected to be less than 1. Right? You don't want it to be less than 1. Right? And I'll show you why. Right? So you have your observed minus expected squared all over expected. The thing is, if your expected is less than 1, let's say your observed in this case is 5. Okay? So 5, and let's make the expected less than 1. Let's make it 0.5. So 5 minus 0.5 over 0.5 is 4.5. 4.5 squared. What is 4.5 squared, somebody? Is it 21, 21.2?
20.25.
21.25?
Oh, just 20.25.
Oh, 20, all right, 20.25, right? And if I divide that by 0.5, that means this number here is roughly greater than 40. That's a big number. So you can see, because the fact that if you're dividing by something less than 1, really what's going to be is you start taking this number and you start doing, you're not taking a fraction, you start doing multiples. So it's this number times 2, right? So if you have x divided by 0.5, it's the same thing as x times 2. So what happens is this has an adverse effect on your numbers, giving you a large number. So you need to be careful. Again, you'll never need to worry about this. This is not going to be on a test. Again, I'm showing you just so you know that you've got to be careful. Your expected value, really, you're going to make sure that it should never be more than less than 1, or you may need to change your model.
Professor?
Student?
I was wondering if you keep the screen share on, like, will it affect the recording?
Yeah. Again, unfortunately, I
Oh, okay. I was not sure. That's why I didn't want to call.
Yeah, no, that's fine. Again, I have so many buttons I've got to press. Right? So to repeat, if the reserve is a 5, expected less than 1, let's say 0.5, 5 minus 0.5 is 4.5 squared all over 0.5 is 20.25 divided by 0.5 is a factor of 2, makes that number very large. So unfortunately, what's going to happen let's say you got 3 items, right? So reserve minus expected. If this is 10 and this is 7, if this is 9 and this is 5, and this is what I used up here, if this is 5 and 0.5, then clearly when I do the chi-square calc, right? This is going to be 10. This is going to be 3. This is going to be 3 squared divided by 7. This is going to be 4 squared divided by 5. So 9 divided by 7, 16 divided by 5. This is going to be 20.25 divided by 0.5. Clearly, this one here is going to be weighted so much more because it's going to be 40. It's going to cause this number here to really be not fair, right? That's the point, right? So again, I don't want to spend any more time on this. This is just kind of a little bit aside, but it should make sense to you. If you go on to data analysis, you want to make sure to understand that. All right, so now let me go back to my screen share. Again, my apologies. I'll make sure to put that together next time. If I don't do it, make sure to tell me. Some of you have me for 222, right? So make sure, again, I'm going to do the exact same thing in 222. Get a lot of screens I'm going to be managing. So make sure, just if I'm showing something that's not clear on the screen, make sure just call out and I'll fix it. I won't take offense. Okay. So so here at our example, here's your observed, your expected, you do this all together, you have your chi-square calc, right? It's 60.99 minus 68 squared. Minus 68 squared divided by 68, right? So again, so here, your chi-square calc is 3.25. So again, 3.25 is your chi-square calc. You can look at your degrees of freedom, right? So how many categories do we have? Categories are, you got 1, 2, 3, 4, 5. So your degrees of freedom are going to be 4. Okay. Let me stop my screen share and let me go to my document camera, right? So again, 0.05, 4 degrees of freedom, 9.49. Okay. So let me get rid of my scrap piece of paper here. .49, where this is 0.05, right? We got a value of 3.25, except HO. In this case, it means it is Poisson with a mu of 0.9. Okay. Now we can also do this with a continuous distribution. I'm not going to go through this exact problem. But you can do the exact same thing if you wanted to know whether something followed a normal curve, right? So again, it's very true. So it's the exact same thing you could do before. So again, you have your observed over here and you have your expected. So the chi-square calc is just the observed minus expected squared all over expected, and you add them all up. Okay? Okay. So again, this would be the way you did this problem where it was being normal. Now again, I don't want to spend a lot of time on this. So one was a Poisson, one was a normal. You're not going to have a problem like that on a test. I just wanted to show you those because basically that's, you know, show the theory that it doesn't need to be something that's a straightforward example. Okay. This next slide, I'm going to take a minute and talk about this. This will not be on the test, but I want to talk about this. This has to do with degrees of freedom. We've learned degrees of freedom are n minus 1, and now we learned about it as being k minus 1. Well, that's not exactly right. Okay? So, I'll come back to the slide in a second. I want to show you on a piece of paper. Degrees of freedom is n minus 1, k minus 1, or something minus 1, and then really it's plus, or rather, excuse me, minus it really is n minus 1 minus the number of parameters not explained by the model or not explained, right? So it's not uncommon to have a degrees of freedom of n minus 1 minus 5, n minus 1 minus 29, n minus 1 minus 122. You could have this. It's always phrased as like n minus 1, then minus something else. So this would be n minus 6. This would be n minus 30. Okay? And again, k minus 1, same thing. K minus 1 minus 3. K minus 1 minus 22, something like that. Now again, you will not see this too often unless you do big data. So let me show you an example. Let's say you've got a distribution, and all of these are all data points, right? These are all your data points. Clearly, they're all clustered together. They're all over the place, right? And let's say your n was 500. You get 500 data points. But then you've got a point up here, and a point up here, a point up here, a point up here, a point up here, a point up here. The computer may do a calculate your degrees of freedom. In your degrees of freedom, they may say your degrees of freedom are 93. Excuse me, 493. Why? Because what it did, it said it was 500 minus 1, and then what it did is it minus all of these data points that are what's called outliers. They don't fit with the data, so we don't like them. So we're going to say 6. So therefore, it's going to be 493. Right? Again, this has nothing to do with this class. I'm just telling you the difference to make sure you understand with degrees of freedom is not really just n minus 1. It's not really just k minus 1. It's really n minus 1 minus the number of parameters that are not explained or need to be explained. Okay? So let me go back to this PowerPoint to show you what I'm talking about here. So in this slide, right, this slide here, if you assume, if you said, hey, data follows the model, data follows the model, data does not follow the model, and we're assuming the model is normal with a mean of 2. Well, officially, your degrees of freedom are, in this case, 6. Again, this is given to you. There's 6 categories, so we thought it would be 5. It'd be 6 minus 1 minus another one. Why? Because with a normal curve, I said this, with a normal curve, you need to make sure you know the mean and the standard deviation. So if the mean is not, if the mean is known, but the standard deviation is unknown, meaning you got to calculate it, you take off a degree of freedom. So in this case, the degrees of freedom will only be 4. If you want even further, say, yeah, we think this follows a model, and the model is normal, but you don't know the mean, and you don't know the standard deviation, then you do 6 minus 1 minus 2, because you need to estimate by using X bar for the mean and sigma and S for the sigma, right? So again, here it is. In general, degrees of freedom are the number of categories minus 1 minus the number of parameters estimated by the data or not explained by the data. Again, this is the official answer of what it means. Okay? All right. So let's do this together. Here is a practice problem on the goodness of fit. So everybody do this problem, I'll do it myself, I'll show it to you. And then that's it for this topic. And then we'll go do the last topic. So take a couple minutes to do this one.
You're muted, Professor.
Let's do this together. Sorry about that. Thank you. The expected percentage, apples 30%, bananas 20%, oranges 50%, equals 1.0. I'm going to check, make sure it's collectively exhaustive. Okay. We have our observed, right? We know that 28 people bought apples, 18 bought bananas, 34 bought oranges for a total of 80. So the expected value is of the 80, if you do 80 times 0.3 times 0.2 times 0.5, right? So 80 times 0.3, our expected is 24. Bananas, 20 times 80 is 16, and 50% clearly is 40. Okay, so again, our HO and H1. Data follows model. Data does not follow model. And our model is this right here. Reject HO, this is step 1. Step 2, reject HO if chi-square calc is greater than, again, it's always going to be a one-tailed test. It's always going to be one-tailed upper. How many categories? 1, 2, 3. So 3 minus 1 is 2. Alpha is 0.05. So again, zooming in, 0.05, 2 degrees of freedom, 5.99. Right? So 5.99. Chi-square calc is going to be observed minus expected squared all over expected. So 28 minus 24. 28 minus 24 squared all over 24 plus 18 minus 16 squared all over 16 plus 34 minus 40 squared all over 40. 28 minus 24 is 4, squared is 16. 16 over 24 is 0.66. 18 minus 16 is 2, squared is 4, 4 over 16 is 0.25. 34 minus 40 is negative 6, squared is 36, divided by 40 is 0.9. So you add them all up, I believe it's 1.81. You want to check me, make sure my math is right.
Yeah, you're correct.
Thank you. So here is my 0.05. My cutoff here is 5.99. 1.81 is here. So accept HO. Distribution follows model. P-value. P-value. Chi-dist. The cutoff. 1.81. Degrees of freedom. 2. I write this again. Chi-dist. 1.81, comma 2.
Professor, what are the parameters that you use to get the value 5.99?
I used 0.05, right? Degrees of freedom. 0.05 is my alpha, and my degrees of freedom were 2 because there was number of categories. It was 3 minus 1.
So the chi-squared table is different from the T
Yeah.
table.
Yeah, 100% different.
And also, so just to clarify, for a chi-squared, it will never be a two-tailed and it will never be a lower tail.
Correct. It can't be because this point is 0 on this table, and never be two-tailed. A chi-square, goodness of fit, is always going to be data follows the model, data does not follow the model. Okay? Thumbs up, everybody get it? thumbs up if you like it. Okay, good. Okay, so now what we're going to do is we're going to go to the next one. This is known as a different test. This is known as the chi-square test of independence. Okay. I'm going to say it again. When you read a problem, particularly for the exam, you need to take a minute to determine what type of problem it is. I've had students in the past that see a problem, and I'll have one student say, oh, this must be a 2-sample test, and do what we did 2 days ago. Another student with the same problem will think, oh, this is paired data. I'll see a third person, they'll say, oh, yeah, this is goodness of fit, chi-square. And I'll have a fourth person say, oh, no, this is chi-square test of independence. Okay. Make sure you can read the problem and determine what type of problem it is. Because if you start doing the problem one way and you get the wrong answer, then you're, if it's a multiple choice problem, a multiple part problem, you're going to get all the subsequent parts wrong. Right? So here is a, I'll say a logic test. If you start doing calculations for a problem, and if the numbers are really wacky, meaning, oh my gosh, I did the chi-square calc, and the calculation is, is 69 million blah blah blah. Well, we've never, nor will we ever do a problem where the chi-square calc is 36 million. Clearly something's off, right? If you're doing a 2-sample test, and again, you're doing the calculating the S sub P, the pool standard deviation, and you're getting a value that really, after you do the square root, you've done something different, and it's not anywhere near the range that you have between the two values. Again, stop yourself. So again, you need to make sure to not just see a problem and power through and just follow formulas. Make sure as you're doing the problem, boy, yeah, this makes sense, or does not make sense. Again, do you understand what it means? You want to be careful about that. Okay, so this is a test of independence. Okay, so here, essentially what we're saying is we're using what's called a contingency table to test whether something variable are independent. Okay, so let me just get right to the problem. Okay, here it's not really a model, we're looking at two variables. So here is an example. The example is, here we've got a we're analyzing the writing in a catalog. We're analyzing how well it was written. Okay, now across the top is someone has said, oh, the writing is excellent, the writing is good, the writing is fair. And then what's on the rows is the amount of sales, right? Whether the sales were below standard or below what was expected, whether they were standard or what was expected, or above. So there were 450 catalogs. 75 of them were deemed as written excellently, and they produced sales. Again, these are online, these are catalogs to buy something. And 75 of them performed, they exceeded expectations as far as their sales. 55 of them were deemed to be, yeah, the writing was so-so, and they performed below what was expected, right? 37 of them, the writing was good, but still had low sales. 65 of them had, poor writing, but yet did more than sales. Good for them, right? So essentially what we're trying to do, these are both variables are categorical variables, and these are levels that are mutually exclusive. And what's in the cells are values or cells are frequencies, or known as counts, right? This is the number of the 75 is the number of catalogs. There's 75 catalogs. 43 is the number of catalogs. So clearly what we may want to know is we want to know, okay, the business question is, gee, does the quality of the copy, the quality of the writing of the catalog, does that affect sales? Right? Logical. Does the quality of the writing in the catalog, does it potentially affect the sales of our products? Okay. So these here are what we have here. These are the actual observed, these are the observed frequencies. These are observed points. So then what we have is we have our HO and H1. Okay. For goodness of fit, there was one hypothesis statement. It is data follows the model, H1, data does not follow the model. For this test, also one hypothesis statement. These are, the variables are independent, the variables are not independent. The variables are independent, the variables are not independent. Independence is always assumed, so that is always HO. Independence is always assumed, therefore that goes HO. So what you are saying, going back a slide, we're saying, you know what? Our initial conclusion is, yeah, they're not related, right? I mean, there's no relationship between how well it's written and the number of sales. They're not related, just not related. Again, that's always going to be what your assumption is, and then you prove there is some kind of relationship. So I'll say again, HO is the variables are independent, H1 the variables are not independent. Or you could say the variables are not related for HO, not related meaning independent, and H1 is the variables are related, meaning they are not independent, right? So it depends on where you use the not. If you say related, the not goes in HO. If you're saying independent, the not goes with H1. Okay, so then what we do, so again, HO is the row variable and the column variable are independent. H1, the row variable, right, are not independent, right? The variables are independent, the variables are not independent. Okay. We're gonna do this test the exact same way we did the goodness of fit. We're definitely gonna go of observed and expected, right? And it's gonna be the sum of observed minus expected divided by, observed minus expected squared divided by expected. That's the same thing. The only difference here is how we calculate the expecteds. The difference in this instance for this topic is how you calculate the expecteds. Okay. So what we have to do is you have to come up with a method of coming up with the row totals. Okay. Now what I'm going to do is I'm going to share, here's this slide and here is this slide. I'm going to show you on my document camera what I mean. It'll be easier if I show you the steps. Okay. What is in the actual, this is your observed. So what this is the total of this row. The 40 is the total of this row. The 20 is the total of this row. So 30, 40, and 20 is 90. The total of this column is 15. The total of this column is 15. The total of this column is 60. And again, 60 plus 15 plus 15 is also 90. Okay. So this observed. If I want to come up with my expecteds, right? The distribution has got to be the same. Again, these are the observed data. I didn't put in the actual values yet. I don't want to confuse you, right? So the expecteds is still to be the same frequency. So this is going to be 30. This row is going to equal 40. This one's going to be 20. The grand total is still going to be 90. This one's still going to be 15, 15, and 60. These are called marginal distributions. Marginal, because of the margins. These marginal distributions must be the same. So to get this value right here, it is row total 30 times column total 15 divided by grand total, right? So what's 30 times 50? What's 30 times 15 divided by 90?
5.
What value?
It's 5.
10?
It's 5.
I still can't hear you.
It's 5.
5? Okay. To get this one right here, same thing. Row total, 30, times column total, 15, divided by 90. Exact same thing. It's going to be 5 again. Now, once I've got these two, this one here, I can get just by subtraction. Because this is 30, 5 and 5. This is going to be 20. This one here, right? Same thing. Row total, 40, times column total, 15, divided by 90. What's that value?
Uh, 6.666.
6.6 is what we get. We'll round at 6.6. Then this one is actually going to be the same thing. So you're going to calculate it again. It's going to be 6.6. What's 40? What's 40 minus 12.2? No, 13.2.
26.8.
26.8.
Yes.
Right, 26.8. So basically, I found it this one. This one I can do just by subtraction. Again, 15 minus 11.6 is 3.4. Right. So I get these two just by subtraction, and then 20 minus 3.4, 6.8. What's 20 minus 6.8?
13.2.
13.2. Right. So basically, now what I've done is I've done my expecteds. So then I can do my chi-square calc by taking this value, blank, minus that value, minus 5, squared, divided by 5. Plus the next one, I take this value, whatever it is, blank, minus this value, minus 5, squared, divided by 5. And I do this 1, 2, 3, 4, 5, I do this 9 times, add them up, and I get a value.
I have a question.
I have an answer?
So like those value in the expected table, aren't they supposed to be integers? Because they're
Thank you.
counts.
Thank you. Thank you. They are not supposed to be integers. They do not need to be integers. Only observed, because the expected values are, again, it's like kind of a weighted average. It's what you're expecting it to get. right? So it does not need to be. And you'll see there's a review problem that you're going to do for tomorrow that has a table that you'll see some values are numbers and some values are, are integers, some of them are not. And you clearly see the expected values are not. Okay. For my graduate students, I'll give them like this table here, and then I'll give them this table here, but I won't label them. And I'll ask them which one. I'll say, I could ask them, this table here, is this observed or expected? This table here, is this observed or expected? This one could be either. This one can only ever be expected. Because why? Because you have fractions for your values, right? Okay? So, based on this, let me go back to the PowerPoint and we'll kind of tie it all together for you. Okay, so again, we looked at our observed there we go, our observed frequencies, right? So the 28, 37, 55 is 120, the 47, 43, and 60 is 150, then 180 equals 450. And again, the column totals, add them up, also is 450. So again, to find the EIJ, or the expected value, so this 40 here is the 120. Again, you should all do this. 120 times the 150 divided by 450. In this instance, yes, it is 40, and it's 40 exactly. But it doesn't need to be. The 32 is 120 times 120 divided by 450 gives you 32. Now again, this last one, you don't need to calculate. You can get it by subtraction. Because you know this column, this row total is going to be 120. So 120 minus 40 minus 32 means this value here is going to be what, 60, 68, 48. Okay? So once you do this, essentially what you'll get is you'll get this table. Notice the circled values are the ones that you get just by subtraction. So you do not need to do the calculation. You can, but you don't have to do the calculation for every square. Okay. So then, once you have your observed and your expecteds, you just do the chi-square calc, right? 28, right, minus 40 squared divided by 40 plus 37 minus 32 squared divided by 32, et cetera, et cetera. So you do this 9 times, add them up, and you get a chi-square calc of 11.56. Any questions? Right? Row total times column total divided by grand total. Okay. Now, you have to do your degrees of freedom. Degrees of freedom in this case are a little different. So you know degrees of freedom as n minus 1 or k minus 1. Now it is the number of rows minus 1 times the number of columns minus 1. The number of rows are 3. 3 minus 1 is 2. The number of columns is 3. 3 minus 1 is 2. 2 times 2 is 4. So your degrees of freedom are 4. So again, going back to our chi-square chart, okay, 0.05, 4 degrees of freedom, 9.49. So based on our problem, our chi-square calc for our problem, I think it was 11.56. 9.49 is the value we found, 0.05, 11.56 is here. You're going to reject HO. The copy and sales are related, meaning not independent, right? So clearly, it does appear that how well the catalog is written corresponds to how well the sales are. Degrees of freedom are number of rows minus 1 times number of columns minus 1. So 3 minus 1 times 3 minus 1 is 2 times 2 is 4. Note, we had defined this cell here, this cell here, this one done by subtraction. We found this cell and found this cell. This is done by subtraction, subtraction, subtraction. The number of cells that you need to calculate is always equal to your degrees of freedom. So our degrees of freedom are 4. You find 4 cells, the rest of it can be done by subtraction. Is this a test question? No, but again, do you understand what it means and will it help you? Let me just finish up on our, okay, whoops. Can you see the PowerPoint, thumbs up? Okay, thank you. All right, so again, the next slide, don't really worry about this. This is basically just, this talks about dependency, all right? All right. Let's do this problem. And after you do this problem, then we'll be done, and then you can take a quiz. So let's do this problem together. I'll give you a few minutes. All right, let's do this together. There we go. Okay. So again, you have the data. Aggressive behavior, boys and girls, 70, 30 for 100, 60 and 40 for 100, 130 for the aggressive behavior, 70 for the non-aggressive behavior, 130 and 70 is 200. So I've checked everything. It makes sense. Our HO and H1, HO is gender and behavior are independent or are related or not related, right? Gender and behavior are not independent or are related. Again, either way you want to have it. Reject HO if chi-square calc is greater than. How many rows do we have? 2 minus 1 is 1. How many columns do we have? 2 minus 1 is 1. 1 times 1 is 1. 1 degree of freedom. Meaning we find this one cell, we get everything else. So clearly this is going to be 100. This is going to be 100. This is going to be 70. This is going to be 130. And this is going to be a grand total of 200. Right? The degrees of freedom are 1. Looking at our chi-square calc, or excuse me, our chi-square table, right? 5% significance. 5% significance at the 1%, 1 degree of freedom is 3.84. So 3.84. Okay? Do our expecteds. So again, row total times column total divided by grand total. 100 times 130 divided by 200, I think is 65. If this is 65, this becomes 35. This becomes 65. This becomes 35. So then our chi-square calc, 70 minus 65 squared all over 65 plus 30 minus 35 squared all over 35 plus 60 minus 65 squared all over 65 plus 40 minus 35 squared all over 35, right? Do this out. I believe this is 0.38. I think this is 0.005, 0.38 again, and 0.005. I believe total is 0.77. Is that right? Do I have that right? Point 3.84, right?
Yeah, that's great.
Thank you. 0.77 is there. So accept HO, meaning they're not related. No relationship. P-value is chi-dist 0.77, 1. Okay. My apologies. We're going over a couple of minutes. Just about ending class now. Again, please take the quiz now if you can. If you can't take it later, I guess. But if you want to take the quiz, it'll help you prepare you for the exam. Okay. Again, I will stay on till everybody kind of signs out. So if you want to ask any questions about stuff, I'll stay on and talk to people. Otherwise, take the quiz, and we'll see you all tomorrow. So tomorrow, before you sign off, I'm sorry, there's something I've got to show you. Excuse me, you gotta stay with me for just a second. Let me do this. I'm going to amend the homework assignment for tomorrow. Can you all see the power? I mean the website. Okay, good. All right. So basically, for homework, there's a couple problems you are not going to do. Very much near the end here. Okay, here we are. Okay, so you will do 120. You'll do 121. You will not do 122. Ignore 122. Okay? And that's, so basically there's only 2 problems you're going to do for goodness of fit. Then you'll do 123 for test of independence. You'll do 124 for test of independence. And then we're going to skip 125. So basically you've only got 4 problems to do for tomorrow. 2 tests of independence, 2 goodness of fit, plus the case of Turnpike City School. And then we will also do the review problems for the exam. So we'll start class tomorrow by doing this stuff, by doing the chi-square stuff, and then we're going to take a break, and then we'll do the review problems for class tomorrow. So you get plenty of homework to do.
Professor?
Student.
When will you be posting the final practice questions?
Right after
resources.
Class, right after class today.
Perfect. Okay. Thank you.
Probably in the next 5 minutes. Okay. All right. So again, please take the quiz now if you can. Otherwise, we'll see you all tomorrow. Thank you very much. Appreciate your patience and going over a few minutes. All in the effort of having fun. Okay.
Professor, have you set for the duration of the exam yet, the final?
I have not.
Oh, all right.
I don't know. Is anything, again, I'm not sure. It may be 2 hours. So it's either going to be 90 minutes or 2 hours, but I'll know that once I kind of get all the questions together, see how long I think it's going to take you to do it.
Oh, okay. So that means if you think it's 2 hours, it's going to be a bit harder than the 90 minutes.
No, not necessarily. It just means there may be more parts, and I'm like, okay, to get this calculation may take you longer.
Got it.
Again, it's probably geared no more than a 90-minute test. I just may give you the extra half hour, so I'm not sure yet.
That's generous.
Yep, I'll let you know tomorrow.
Regarding chi-dist, on the test, we can't just write chi-dist, whatever, right, for the p-value. We have to calculate it out. I can't hear you, Professor. Professor, I can't hear you.
Yeah, no, it's gonna be an Excel command.
Okay, so we just have to type out chi-dist and then.
Yeah, exactly. It's exactly what I did for you. Again, there's no. I would never show you something, write it down without you calculating it. So again, I've only showed you how to do chi-dist. Chi-dist, just like the t distribution, you can only you can kind of figure it out if you have a calculator, but it's too complicated. So again, just give us the Excel command.
Mm-hmm.